studio here. Yeah?
Okay, so last speaker of this categorical session is Paul-André Méliès, who will talk about categorical combinatorics of scheduling and synchronization in game semantics.
Okay, so the question is, can we understand logic in space and time? So imagine you see these two people here, Eloise and Abelard. They discuss, and we want to understand what are the principles at work in such a dialogue, in such an interaction. And clearly there is time, but there is also space. And the purpose of this talk is to understand how different proofs and programs may be combined together in space, typically concurrently, and synchronized together in time. And I will work in the rich and modular ecosystem provided by linear logic and, game semantics, okay? And so I will focus on game semantics and try to understand what are the hidden principles of this game semantics. And so the starting point is very easy. It's defining the simplest possible notion of game, and I will call them template games. So the idea is we start from a very, very small category with two objects generated by these two edges for opponent and player move. And this little category will play a fundamental role in the talk, so please remember it. The reason is that, and this is inspired by the notion of coloring in graph theory, I will define a game simply as a category, A, together with a functor to this specific category, which you can see as some kind of category of labelings. Okay. And so typically, the objects and morphisms of the category A, I like to call them positions and strategies, because I like to think of the category as an unlabeled transition system, which is then labeled thanks to this functor into my template of games. And so this functor, I will call it polarity functor. What it does, it transports every position of the category A into a polarity, positive or negative, okay? Plus or minus. But it also enables to define a move of the game simply as a trajectory, which is mapped into an O edge, okay? And similarly, a move by player is simply a trajectory which is mapped into the P edge, okay? It's very easy. But there are also silent moves, like in process calculi, which are the trajectories which are mapped to an identity. So typically, if you are a silent move, you don't change the polarity of the position, okay? Clearly. Okay. That's it. That's a game. And I think it's difficult to make a simpler definition. But now the question is, what is a strategy? And so a strategy between two games will be defined by another very small category. So it's a category with three objects generated by this graph. Okay? And this graph contains 4 different edges. And so we will need to understand what these edges mean. And, well, it's kind of easy. We try to define a strategy between A and B. And so there are opponent and player moves which are played in A. And there are opponent and player moves which are played in B. And so S and T here means source and target of the strategy. And I like to represent these edges here, OT, PT, PS, OS, using some kind of tile notation. And so typically OT here is this, and you can think of it as a move. We will see that here. So if I take a sequence of, this sequence, OT, PS, OS, PT, I get that picture, which represents the idea that there is an environment, a move by the environment, which is transmitted here, and then a move by the environment opponent, which is transmitted here. Okay, it's very simple. Okay, so this picture is just to represent this trajectory of length 4 in my little template of strategies. Now, the beautiful point is that, in fact, there are, this category here, which I call the template of strategies, is very small. Remember, it only, it's this one, okay? It's very small. But it contains 2 functors into the template of games. And the functor corresponds to projecting on the first component or second component. And it's nice to see it in a diagram like this. If you take these 4 edges, which I've represented here, the source projection, we just look at what happens on the left, and the target projection will only look at what happens on the right. Okay, it's very, very simple, very easy. Okay. Now, what is a strategy between two games? Well, it makes sense to define them as spans. So spans is a nice generalization of relation. So a span is simply a category S, which I will call the support of the strategy, together with the functor, a source functor and the target functor, which map into A and B. Okay? But moreover, not just that, also a scheduling functor, which maps the support of the strategy to the template of strategies. So let's see why. The reason we want to have this extra little information is that we ask that this diagram here commutes. And so what does that mean? Imagine I have a trajectory in the strategy, in the support of the strategy. It is mapped by source and target into trajectories in A and B. And then these trajectories are polarized by these two functors, lambda A and lambda B. So what this functor here does, it explains it describes how the two trajectories in A and B are scheduled by the strategy, okay? And so remember, this information here is about describing, what moves happen on the left and on the right in time, okay? And so we see this idea that here, this functor here describes the time structure, the scheduling structure that relates the two projections of the trajectory on A and B, okay? So it's extremely simple and also completely, we will see, in the mood of internal category theory, okay? I'll come back to that. But you see, it's very simple. So just a very basic diagram. Now, yes, I just for terminology, this category S, I call it the support of the strategy. And so if you look at the trajectory in this support, which plays, these polarities in the template of strategies. So it's OT, PS, OS, PT. It's typically what is represented in traditional game semantics as this. So there is an opponent move in B, then a player move in A, an opponent move in A, and then a player move in B. But this representation is more mathematical in a way, okay? And so this enables to draw things in a kind of more precise way as these four, so here we have these four moves, M1 here, N1, M2, N2, where this is opponent, player, okay? And now that we have defined strategies, we want to define simulations between them, and it makes sense simply to say that it's a functor between the support, which makes this three little triangle commutes. If you think about the definition, this is the only possible one. And the nice thing is now that if I fix two games, okay, I obtain a category of games, okay, whose objects are strategies and whose morphisms are the simulations, okay? So that means when I fix a game A and a game B, in between, I have a category of strategies and simulations, okay? And so clearly, this leads to the idea that we should try and build a two category, okay, or bicategory of strategies. And this is what I will do now, okay? And this is where things get really surprising and exciting. And so the idea is we want to take this family of categories, okay, of strategies and simulations, and connect them to build a bicategory. And really what this means, okay, this categorical jargon, is that we want to define the composition of two strategies. I have a strategy from A to B, a strategy from B to C. I want to plug them together to let them interact so I get a strategy from A to C, okay? And clearly, before I compose, this is the shape, okay? I have a strategy from A to B, a strategy from B to C. I have the support of sigma, I have the support of tau. And then there is this stuff which is a bit mysterious, which describes the schedulings of sigma and tau, okay? And so the kind of miracle is that we will compute this pullback here, okay? So this pullback here, and we get something interesting. It was not at all expected, but it is interesting. And this pullback, in fact, I call it the template of interactions, is a category which contains 4 positions, and here there are 6 edges. And really, you can draw them like this. So they describe how a strategy sigma can interact with a strategy tau on an interface. So sigma, and so here tau could play like this, without any interaction with sigma. Sigma could play like this with no interaction with tau, but also sigma and tau could interact together. I tell you something, and then at the same time that I tell you, you listen. Yes? So this is a moment of synchronization, and this is exactly what happens here and here. Okay? So this is the interface between the two, and again, it has to do with space and time. How you schedule, how you synchronize two people. It's not easy sometimes, yes? But here, because if I look at this, for instance, this trajectory in that little category, okay, OT, this one, okay, I get this picture, which really describes how a strategy sigma and a strategy tau could interact on their interface. So the interface is here, okay? And okay, it looks nice and interesting, but the miracle really is that there is a functor, which I call hide, which will transport this category of interactions into the category of strategies, okay? And this hide will define composition. And okay, you can define it. It's in the title there is combinatorics. So everything is very combinatoric. I mean, very precise. And it's important for game semantics because game semantics is complicated. So it's important to have very good combinatorics to manipulate that. But if you look at the picture, it's even nicer because you see here it's a sequence in the template of interactions, which is mapped by hide into a sequence of in the template of strategies. And you see here what it does is simply erase the OP and PO moves, which are turned into identity because nobody knows what happens inside. Okay? And that's why I call the functor hide. Okay? It hides what happens in the middle between sigma and tau. And so from that, it's very easy to adapt the traditional definition of composition of spans into composition of strategies. So you start by defining the composition of the spans that we had here between S and T. And so here you can think of this as a synchronization of the two supports. So the two strategies, sigma and tau, they will synchronize on the game which I've shown you here. Okay? So this is this pullback. But now, the extra thing that game semantics asks for is that you compose this thing with this functor hide. Okay, so you get that by universality property. So that means when you synchronize the two strategies, there will be a map into the template of interactions, and then you hide everything which was inside. Okay, and then you get a new strategy, and this is your composition. That's fine. It's nice. And so this says that composition is really synchronization, which is the pullback of the span, and then hiding, which is this little extra functor which I've shown you here, which hides the internal moves of the strategies. That's nice. But what is even nicer is the apparition of the copycat strategy. So the copycat strategy has always been a nightmare for people who want to do things well, because it seems like really a definition based on transition systems, and you need to be careful. It's difficult to extract the true structure and meaning, but here we have it for free. So the observation is that, in fact, there is a functor from the template of games, okay, which is, remember, only two states, and OP, okay, to the template of strategies, which looks a bit more complicated, because it was like OP. Okay, so how do you do that? So you need to do something which is taboo in transition systems, which is to turn one edge into a trajectory or a path of length 2. Okay, so you break the usual invariant, which says that an event or a transition is turned into a transition. And so the little functor here, what it does is very simple. It takes a polarity minus or plus and turns it into a polarity minus or plus plus. And what is more important, it takes a move, opponent move or a player move, and turns it into a path, a play of length 2. Okay? And so typically this opponent edge is turned into this path, and this player edge is turned into this path. And just with that, we can define the copycat strategy. It's simply defined as the polarity functor, which, remember, which polarizes every move of the game A here, either player or opponent. And now the copycat functor will turn any of these moves into a very small play of length 2. Okay? So it's a very cute transformation. And then, just as previously, we get for free the copycat strategy. Okay? And so now, the very unexpected discovery that emerges from all that work. Okay? So you play, with these little categories, and you say, okay. Then suddenly you realize, oh, but my God, the reason why we have a bicategory, okay, in the end of games, is that in fact the categories I've shown you, they are very, very small categories with 2 objects, 3 objects, 4 objects, super simple. Well, and the span of functors and the functor height and the copycat, this very small thing, is in fact something called an internal category. Okay? And here, another way to say it's a double category. It's something completely simple, much simpler than the bicategory of games and strategies and simulations. And the point is that just from that observation, as an immediate consequence, essentially, you get that the construction defines a bicategory of games. And we know that it's very difficult to construct these animals, okay? And so it's a good news. And moreover, you can show that this bicategory is symmetric monoidal, and that is, in fact, it's star autonomous, okay? Just by the same recipe. And that's also something which is quite nice and pleasant. So each time you want to add a structure to this bicategory, what you find is, in fact, that you need to construct internal categories. So for instance, here, the internal category of tensor products together with a span of internal categories, okay? And so here, this functor here, what it does, it picks the good polarities, and this one, it gives a new polarity to the position you've computed. And so typically, yes. So typically here, for the tensor product, we have the 2 games, and they are multiplied independently. And what the tensor product does, it picks the good polarities and rejects this polarity minus minus, which is the usual thing and the good thing to do in that kind of situation. And Pince will take this little thing that we had and pinch it. Maybe I should pinch it to get this little polarities that we wanted at the beginning. Okay? And so the conclusion and future work is this. So here it's games played on categories with synchronous copycats. Okay? There is an easy recipe to construct new game semantics. So once you have the framework, you just need to check a number of little things, and you know that you have a good new game semantics. So in the paper, I consider 3 small templates, one for alternative games and strategies. This is the one I've shown you. One for concurrent games and strategies. So you will find it in the paper. And one for functorial spans, which is the simplest version. And something also very important for me is that the principles I use, in fact, emerged from my work with Leo Stefanesco on concurrent separation logic. And so it's the same principles. And moreover, recently, I built a model of differential linear logic, which interestingly integrates ideas from homotopy theory. Thank you. Yeah.
So thank you, Paul-André. We have time for questions at the back of the room.
Do you have such a nice explanation for exponentials with
Yes, so you see, what is very pleasant here is that we work really just as independent types, okay? If you think about it, a game is just a support depending on 2 types, okay? Which are these very simple types. And so the idea is to take these templates, so typically the template of games, which is very simple with 2 polarities and OP, and take the bang on it, which is the free symmetric monoidal category. And then when you are there, you get words of plus or minus. And so what you do is simply extract from this, this category, which is the, okay, so you pick from theme of this template of games, okay, so words plus, plus, minus, minus, plus, plus. You pick the ones which are of the form plus, 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 or plus, plus, minus, plus, 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 one minus at most, yes? And from that, you can give a polarity and you recover a very nice exponential modality. And what is interesting is that to define the identity strategy in that case, you need to do something like in homotopy type theory. So you need to have a replacement of the original copycat. Or if you don't want to have it, you need to ask that the underlying category is right proper. Okay, so there are little technical things. But in the end, this says that game semantics is, it seems, is getting closer to dependent types. Okay? And at least internal categories are really a structure of dependent types. And so I'm quite optimistic here.
Hi. So just a curiosity. So you mentioned, you mentioned double categories in relation with symmetric monoidal bicategories. Are you using Mike Schulman's construction, or is this completely unrelated to that?
No, it's okay. So maybe there is something interesting. Is that in fact the drawing I do here, they are really like, for instance, this one. You can think of them as little, squares which are tiled exactly like in a double category. And so really the structure, the multiplication, so the hide operation is telling you when you plug these tiles, these square tiles, how you compose. Okay, and so it's quite nice that we see the fundamental structures of strategies. And here I speak about sequential strategies, but it's also possible to do that for concurrent strategies or other animals. Are in fact based on the this very simple description, again, not of the strategies, but the shape of the strategies. Okay, so it's something very important for me. It's like a type, but even more precise. When I meet you, okay, I know that I should let you speak first, and then you will speak. You will speak, and then I will answer. It's a fundamental structure of how we plug and play. Okay, how we like we discuss, and someone else comes, and then we start to interact. And all this very fundamental structure of language and dialogue are inside this little thing. The fact that this defines a category or an internal category, and from that you get the bicategory. And so I think this, together with the connection with systems like concurrent separation logic, I hope we're getting to an old dream by Milner, which is that we can use synchronization algebras, and mix them with category theory. And this is essentially what I'm doing here, nothing more.
Okay, we have time for one last question. If we have the audience, yeah.
I'm curious about the concurrent games, because I had the impression that in the definition, so a game was a functor from a category into this category of games, which assigns to every position like a polarity, whether it's a player or opponent position. And in concurrent games, positions don't have a polarity, right? Because
And so it's good you ask me. We could have prepared that even, probably. So the idea is, instead of starting from the template I've shown you for sequential strategies, you start from a category with one object, because there is no polarity in concurrent games, and then two moves, or shapes of moves, opponent and player. And then the category which describes strategies, so the template for strategies, looks like this, like a little flower. And in fact, these equations are simply saying that this is a commutative monoid. And in fact, a commutative monoid generated by a number of moves. So for instance, here you have opponent player, and here you have opponent player, but on the left or on the right. And so typically the source and target functors or homomorphisms are just doing that kind of things. And I should mention something. So I mean, this is a definition, and it will correspond to something natural. Where it's like concurrent games with a synchronous copycat. And so, by the way, it's an opportunity. So in my list of talks, or I mean, no, in my list of papers, there is this talk this afternoon soon, where there will be also the description of a synchronous copycat. And I think the idea that in concurrent games we can have synchronous copycats is important, so it should be supported. So if you want to go and watch Nabucco and Simon, is good.
Okay, so let's thank the speaker again.